You know that gray metal box, right? The one that's usually tucked away in a basement or a utility closet? We walk past it every day. But inside that quiet, unassuming box is this incredible world of controlled power, and it's all governed by a set of totally invisible rules. So let's open it up and see the hidden science that keeps all that power in check.
I mean, the stakes here are incredibly high. On one hand, this box is the heart of a building's entire electrical system. It's what powers everything. But on the other hand, just one little failure, and you're looking at a catastrophe. The whole thing is this constant balancing act between incredible utility and very real danger.
And that's really the big question we're digging into here. What's actually going on in there? It's so much more than just wires and switches. We're talking about material science, we're talking about physics, and some really meticulous design, all with one goal: to stop electricity from going where it shouldn't.
Our journey starts with the system that moves all this energy around. You can think of it as the main highway network running right through the middle of the panel.
This is the busbar. Now, it's not a wire, think bigger. It's a solid, heavy strip of metal. Its entire job is to be the central point where all the incoming power gathers up before it gets sent out to all the different circuits. It is, quite literally, the backbone of the whole panel.
Now, the material this busbar is made of is a perfect example of a hidden engineering trade-off. You'd think, copper, right? It's the best conductor, case closed. But not so fast. If you're in an industrial plant with sulfur vapor in the air, that copper can form these oxides that actually start to choke the flow of electricity. And that's where aluminum suddenly becomes the smarter choice. Yeah, it has to be a little bigger to carry the same current, but it's more stable, and get this, when it oxidizes, it creates its own protective layer. So the choice isn't just about raw power, it's about reliability in a specific environment. Okay, so with all that energy flowing through the bus bars, you obviously need something to hold them in place and make sure they don't touch anything else. Let's meet the unseen safety guards. These are the insulators, and their job is, well, beautifully simple. Stop electricity dead in its tracks. They're physical barriers, usually made of something like porcelain or glass, that just don't conduct electricity. And they're absolutely crucial. They make sure the current stays on that bus bar highway and doesn't take a deadly detour through the metal panel itself.
So you see, they do a lot more than just sit there. They provide physical support, holding those heavy bus bars steady. They isolate specific lines, like the neutral. And maybe most importantly, they create a safe separation between the live conductors and the grounded metal box that you might one day touch. They have to be incredibly tough, both physically strong and electrically resistant. Okay, this is where things get really fascinating. We've been talking about physical contact, but high-voltage electricity, it has other ways of getting around. It can literally jump right through the air. So how on earth do engineers stop something they can't physically block?
Well, to answer that, we have to look at the two main invisible pathways that electricity can use to escape. These are the escape routes that engineers are always thinking about. The first route is the most dramatic one. It's a sudden, violent arc of energy, basically a miniature lightning bolt right there inside the panel. And the defense against that is something called air clearance. It's literally just empty space. A carefully calculated gap. If you make that gap wide enough, the voltage just isn't strong enough to make the jump. And it's kind of a brilliant idea when you think about it. Sometimes, the most important safety feature is nothing at all. Now, if the first escape route is a dramatic jump, the second one is much, much sneakier. It's not a leap, it's a slow, persistent creep of current along a surface.
This sneaky path is blocked by a principle called creepage distance. To get this, just think about spilling water on a countertop. It doesn't just stop, it finds a path, right? It'll snake around things. Well, electricity does the exact same thing along the surface of an insulator. So to stop it, engineers have to make that surface path incredibly long, often by adding ridges and fins, to literally make the journey too far for the current to complete.
And this right here, this is the fundamental rule that ties those two ideas together. It basically says that the winding path along a surface can never be shorter than the straight line jump through the air between those same 2 points. It's a simple geometric fact, but it's a critical one for safe design. That straight line is your absolute minimum.
All right, so we've got these perfectly engineered distances, these safe gaps. But what happens when an enemy gets inside the system and turns those safe spaces into dangerous bridges? That enemy is contamination. And we're talking about anything from industrial soot and metal dust to just plain old salt in the air. But here's the real kicker. Even something that seems harmless, like regular dust, becomes a huge problem the second it gets a little damp from moisture in the air. Suddenly, that non-conductive layer of dust becomes a conductive film, and it completely messes up those critical safety distances we just talked about.
So here's the chain reaction of disaster step by step. First, dust and grime settle on an insulator. Then it gets damp. That dampness creates a conductive shortcut for the electricity, a new, much shorter creepage path. And finally, tiny little sparks, called microarcs, start to form across this new path. These little sparks literally burn the surface of the insulator, leaving behind carbon tracks. And since carbon is conductive, you've now created a permanent burned-in failure that will only get worse over time.
So, now that we know the parts and we know the dangers, let's see how it all comes together into a blueprint for a safe, reliable system. And if there's one thing to take away from all of this, it's this right here. A safe electrical panel isn't just about having high-quality parts, it's about the meticulous management of the empty spaces, the air clearance, and the creepage distances. Safety literally lives in the gaps. And you can see how these big ideas translate into very real, very specific rules. Like, you can't just drill a hole in a busbar that's bigger than 1/3 of its width because it compromises its strength. Connections have to be perfectly aligned to prevent dangerous vibrations. And you have these strict rules. Insulate the live parts, but the earth busbar has to connect directly to the panel's metal body for safety. Even the color codes, red, yellow, blue, are a critical part of this blueprint, making sure a technician knows exactly what they're dealing with.
So we've gone pretty deep inside the box. But why does understanding all these fine details really matter to us?
Because these exact same principles, busbars, insulation, clearance, creepage, they're all scaled down and used in almost every single piece of electronics you own. You know that cheap, uncertified phone charger that gets dangerously hot? It's almost certainly failing because its manufacturer cut corners on these very rules. The science of keeping electricity contained is universal, from the power grid right down to the plug in your wall. It really makes you think, doesn't it? How much do you trust the invisible engineering in the devices you use every single day?